Hello everyone. My name is Muhammad Hakimi bin Muhammad Sahring. Method number B0822100241. As an assignment for digital signal processing subject, we have given task which is require our group to do a study about windowing filter, then design windowing filter. We need to choose two window filter, then demonstrate and explain it. We have decided to choose rectangular window and Bartlett window as our topic. So, as introduction, let me give some brief information regarding filter and windowing filter. First of all, filter are fundamental tools in digital signal processing, enabling the manipulation of signal component based on frequency. Finite Impulse Response (FIR) filter are particularly valued for their inherent stability and linear phase properties, which preserve the waveform integrity, a critical aspect in various applications. However, designing an ideal filter often involves infinite impulse response, which are impractical for real-world implementation. To address this, windowing techniques truncates this infinite response to finite line, shaping the filter frequency characteristic. This video will focus on two such a windowing method, the frequency response. This video will focus on two such windowing method, the rectangular window and Bartlett window, examining their design process, frequency response, and practical application. The aim is to evaluate their trade-off and guide the selection of the most appropriate windowing method for different scenario.
Hello everyone, my name is Sharvin Ganesan and my metric ID is B0822104445. Today I'll be talking about the background of our assignment. So we'll start off with filters in digital signal processing. In DSP, filters are employed to enhance or suppress specific parts of a signal. FIR or FIR filters, characterized by a finite impulse response, are preferred in scenarios where phase linearity and system stability are crucial. Unlike the infinite impulse response (IIR) filters, FIR filters do not rely on feedback, ensuring stability and a predictable phase response, which makes them suitable for applications requiring precise phase fidelity. Next, let's look at windowing techniques. Windowing involves multiplying an ideal infinite impulse response by a finite length window function to create a realizable FIR filter. This process affects the filter's frequency response, particularly the main lobe width and side lobe levels. This characteristic influences the filter's ability to distinguish between closely spaced frequencies and its attenuation of unwanted frequencies.
Hello, my name is Muhammad Azhar bin Abdullah and my metric number is B0822100408, and I will cover about the simulation and the MATLAB coding. So as we can see here, for our window, rectangular window coding, the first one is we have to set up the parameter, which is sampling frequency, cutoff frequency, filter order, and the time vector. And then we generate noisy signal, where the noisy signal is 50 Hz sine wave, and the Gaussian noise is 0.5 standard deviation, and the noisy signal, which is the sum of signal of sine wave and noise. Then we normalize our cutoff frequency. We start up with a frequency cutoff over frequency sampling over 2. And then we apply the rectangular window filter using our filter function. Then we apply the filter with filter signal rectangular. After that, we plot the noisy and filter signal. We got 3 plot, which is comparison of the filtered and noisy signal, and then the filtered signal of frequency response, and the filter signal of the impulse response. This is the expected result of the simulation. The first is the filter signal, which is a cleaner version of the sine wave with most of the noise reduced. The filter signal demonstrates the FIR filter effectiveness in attenuating noise component above the 100 Hz cutoff frequency. And the second one is impulse response. The impulse response show evenly distributed coefficient corresponding to the rectangular windows. The rectangular window does not taper the filter coefficient, which leads to the aforementioned ripples in the frequency response. And the third one is the frequency response. A magnitude response with a passband frequency below 100 Hz and a stopband frequency up to 100 Hz. The passband show good preservation of the 50 Hz sine wave. The attenuation in the stopband reduced noise contribution above the 100 Hz, though the ripple effect could slightly impact performance. Overall, the FIR filter successfully attenuates high-frequency noise, enhance 50 Hz sine wave. The filter linear phase nature ensure no phase distortion, preserving the waveform shape. And the second one is Bartlett windows. For the Bartlett window, the same as the first one, we have to initialize the parameter for our sampling frequency, cutoff frequency, filter order, and the time vector. And then we go to the noisy signal generation. Here we declare our signal with 50 Hz sine wave, the noise with 0.5 standard deviation, and a noisy signal, which is sine wave plus the noise. After that, the FIR filter design, where we set up the normalized cutoff frequency, where the Nyquist frequency is frequency sampling over 2, which is 1. After that, the filter application, which applies the design Bartlett window based FIR filter to the noisy signal using the filter function. The next one is time domain signal. Start with the subplot, where we will display the noisy and filter signal for the comparison in the time domain. After that, a frequency response, which compute and plot the magnitude and phase response of the filter. And the next one is impulse response, which will display the filter coefficient in the time domain. And this is the expected output result for the Bartlett windows. The first part is the noisy signal and the filter signal of the Bartlett windows. At the noisy signal part, it's display the noisy signal in the time domains, and the Gaussian noise causing the sine wave to look irregular and noisy. When the filter during with the Bartlett windows, we display the filter signal after we apply the FIR filter with the Bartlett window. One of the characteristic is the 50 Hz sine wave, which should become smoother. The noise should be significantly reduced, particularly in higher frequency component. If this Bartlett window is designed effectively, the low frequency are retained. The high frequency is attenuated. We can verify the degree of noise reduction by visual comparison with the noisy signal. And the second one is impulse response of the Bartlett filter. This part displays the filter coefficient in a time domain. As we can see here, one of the characteristics is a triangular shape representing the Bartlett window applied to the filter design. To ensure the symmetry of this filter coefficient, and we also can check the smoothness of the coefficient. Abrupt transition may indicate issue with filter stability. To ensure the symmetry, we will have to give the filter order an even number. And the third one is the frequency response. The frequency response display the magnitude and phase response of the FIR filter, and the characteristic the magnitude response should show a flat passband up to the normalized cutoff frequency, which is 100 Hz, a transition band around 100 Hz to 150 Hz, and attenuation in the stop band frequency, which is above 150 Hz. The phase response should be approximately linear as FIR filters are phase linear.
Hello everyone, my name is Muhammad Abrisam bin Yusuf. My metric number is B0822210389. Today I will talk about real-life application. Real-life application have two window application, which is rectangular window application and Bartlett window application. Okay, first, rectangular window application. The rectangular window is often utilized in application where computational efficiency is crucial and the tolerance for spectral leakage is higher. As example, is in simple data smoothing tasks where the primary concern is to average out rapid fluctuation without stringent requirement on frequency discrimination. Okay, second, Bartlett window application. The Bartlett window finds its use in application like speech processing and audio analysis, where reducing spectral leakage is essential to accurately capture frequency component. It is particularly beneficial in scenarios requiring moderate side-lobe suppression while maintaining reasonable frequency resolution. Okay, next. For quantitative comparison. Quantitative comparison have three characteristics, which is main loop width, side loop attenuation, and computational cost. For rectangular window, main loop width is narrow and side loop attenuation and computational cost is low. For Bartlett windows, main loop width is wider, side loop attenuation is high, and computational cost is moderate.
And with that, we have reached the end of our assignment presentation. So let me close it off with a summary of what we have discussed. So in this assignment, we have analyzed the design and characteristics of FIR filters using rectangular and Bartlett windows. While the rectangular window offers simplicity and narrow main lobes, it suffers from high side lobe levels. The Bartlett window provides improved side lobe attenuation at the cost of a wider main lobe. Selecting the appropriate windowing technique requires careful consideration of the application's priorities, balancing frequency resolution and spectral leakage suppression. Thank you.